And now let me introduce Nathan Russell, who is a PhD student in our new computer engineering program, who will talk a little bit about error correcting codes. No, mathematical coding theory. So take it away, Nathan.
All right, thank you, Dr. Finkel. Let me see if I can get my screen shared here. Can you guys hear me fine?
Yes.
Okay, I assume you can see my screen as well, right?
Yes, that looks good.
Okay, so as Dr. Finkel said, I'm a brand new PhD student to the department. I'm very excited about starting in this program. I wasn't aware that it was a new program. I found it on the webpage and I was looking for a PhD program to enter, and my experience has been very positive, and I'm enjoying the classes that I've got, and everybody has been very welcoming so far, so I appreciate that. My talk that I'm doing today is about the title's a little bit misaligned here, so before we get here, I'll explain why the screen we're looking at here. So I didn't do a Beamer slideshow, and the reason is because I've taught mathematics for a number of years. And so what I've noticed is that sometimes whenever you have like a static thing where people can't go through, maybe you might say something that somebody wants to back up and look at. You might maybe pass it up. So with this so I'm going to do the presentation from the website. I know that may seem like a little bit um, strange. Actually, let me send this to. So if anybody wants to look on the site beyond what I'm doing, feel free to go ahead and look at it. I just sent the website in the chat. Okay. So as I said, I've been a teacher for mathematics for a number of years, and before I started this program, and I always noticed that some students have a question, or maybe I was going too fast. So what I try to do is make my presentations and all that in what they call the Cornell style of notes going forward. And so it makes it a way where I've made it kind of modular where I could reuse notes based on various presentations and other things. So that's the reason for this site. So my motivation for doing this um, talk is whenever I got the email from Dr. Finkel, I was very excited about the talk because we haven't really had an opportunity to really introduce ourselves to each other. And I thought maybe this would be a good way for me to introduce myself to everyone because I'm very eager to get engaged in research as soon as possible. And hopefully, maybe this might lubricate the gears of communication. So, the prerequisite for this is just a love for the abstract, right? So, some of these things we're going to talk about are not necessarily all that practical, like what you might see in actual machine use, but it has an enormous amount of tools as far as the way it links to other abstract notions in mathematics. Now, so this is an abstract version of coding theory. So the first thing that I'm going to do is I'm going to go through these little prompts here. So the very first question that probably everybody has is what exactly is a code? So as I go through, I'll make that screen larger. You guys can go through as you see fit. Can you guys see that screen okay? The font, I can increase it if necessary or if it's legible.
A little bit of increase would be good.
Is that better?
Better.
Yeah, that's okay.
Okay. So when we say a code in mathematical coding theory, the words outside of context, it may not mean much, right? So we're talking about an actual vector space in mathematics when we talk about a coding theory. We're talking about a vector space that usually has some sort of metric defined on it. And these metrics are often very simple, but it's still just a vector space for the most part, which means it's going to be generated by a matrix. There are coding theory things that are not matrix based, but they don't have the same structure, so we won't be talking about those. So we say let that calligraphical C be a vector space over the finite field of two elements generated by the matrix G below. And so this matrix right here, the very first one you say G equals 2 is actually the Hamming code. It is the linear representation of the Hamming code developed by Richard Hamming. And if we look on down at the next matrix, we'll see that it actually, if I put a little dividing bar there, we'll see that it's actually the identity matrix augmented with another matrix on the right-hand side. The left-hand side is going to generate what we call the information set. The right-hand side is what we're going to call the redundancy set. All right. So G functions as a linear map from the vector was 4 coordinates over GF2 into the 7 coordinates over GF2. So it generates 16 elements. And we've listed those elements explicitly below. Now, when you see the Hamming code represented, there's a lot of people. Sometimes you guys in computer science, I know you'll hear the word circular a lot when you talk about error correction. If I was to arrange these uh, vectors in a way, you'd probably see that circular tile style look to it. But the way I have them, it's not really obvious. All right, so we need to get some definitions and labels out of the way. If you guys are familiar with encryption, we say we pop data through, and then once it's encrypted, we call it ciphertext, and then we say decrypted goes back to the original data. So we add these words because we're going to be talking about whether or not it's encoded or whether it's not. So after a chunk of data has been encoded into the error correcting function, we call it a code word. So every C in the code has 7 coordinates in the Hamming code. So that means it is length 7. We represent the length by n traditionally. The linear map, G, transforms it. It's basically an injective map that with the 4 coordinates. So that means the dimension is 4. And the distance. Now notice that every word other than the initial 0, every code word in that set of the code has at least 3 non-zero coordinates. There's some that have 4, but the minimum is 3. And so we say the minimum weight of this code is 3. And so we put the coordinates together to call it the Hamming code. We say it is the linear 743 code, and it's called the Hamming code named after Richard Hamming. Okay, so if we go back to the next prompt here, we say, are these related to error correcting codes as we know it in computer science? Well, the short answer is yes. And it actually functions kind of like the angular gyrus of a computer. So imagine that you're sitting inside of a talk. And again, I'm brand new to computer science compared to most of you guys, so I don't know who knows what. But every time I give this talk in a math department, I usually have to give some sort of explanation about error correction, whether it be theoretical or in the applied version. So bear with me if I bore us on this. So imagine you walk into a place and you overhear the speaker say, think of the time when you overcame or conquered a turtle in your life. Well, I mean, you're going to have a physical altercation with a turtle. Surely that's not what he said. Well, it turns out that you misheard him or he misspoke. But in either case, you were able to determine what he meant and you were able to correct that error in your own mind. That's a function of what we call the angular gyrus in our brain. Well, what if you heard somebody say, well, lirem ipsum fubar? Well, did you actually say something? I can't understand that. So you actually had to say, could you repeat that? So what Richard Hamming actually did was give a computer the ability to actually correct errors without the need for recalculation or retransmission. And if we think about the error correcting codes on like the Voyager satellites, I think the last time I checked, the Voyager satellites take 17, 18 hours to make a one-way trip back and forth. So I mean, to say repeat what you said is quite of a mishap, I guess. So our mathematical linear code's essentially the same. So I didn't really answer that question yet. I just said yes. So it actually depends. The quick answer is yes. However, the implementation may look very simple. Whenever we have something in mathematics that appears in application, more often than not, the application is usually a special case of a more general method. And most of the time we have error correcting codes use an application like the Hamming code or whatever in memory or whatever. It's usually a special case. Now, as we say, there's no such thing as a free lunch. I heard Dr. Trasinski say the other day in class, I think Milton Friedman was the one that said that, or he's at least credited with that. You know, there's always a trade-off. These special cases are often not super efficient relative to their size. That means that there are better codes, but they may not run as fast in real time. All right. So here's how the general method works. You take the code words, and if we want to imagine what we would be doing if we had to use any code, forget the Hamming code or special cases, the general method would look like this. You use the generator matrix G to run it through the matrix, and it would encode it into a 7-bit code word. Well, that would be transmitted through a noisy channel or stored on some maybe unreliable disk. And the target receives the code word or reads it and performs a Boolean AND operation on every code word in the code. Now that will create 16 different results. And one of these three situations will occur if only, and this is speaking specifically about the Hamming code, if only one bit was altered, that means there'll be a single instance where the Hamming weight, which is where you take the distance from zero, or the Hamming distance, which is how many places that the two code words, the original and the one you're comparing against, differ, there will be one single instance that is less than the minimum distance. If it's zero, that means there was no error. If it's less than one, which is what the Hamming code is able to correct, then it can correct to the single code word. If two bits were altered, it won't be able to correct the error, but it will be able to detect it. The reason is because if you think of like shooting a bullseye with maybe a gun, imagine that you missed the bullseye so much that you actually got in between two bullseyes. You know that there was an error, but you're not able to decipher. In this case, you'll have two code words with the same minimum, same Hamming distance between them. All right. So we say that G is in systematic form, and if we have three or more bits altered, well, then you're going to get a falsely corrected code word. It means it's actually going to be so far off that you hit another bullseye that wasn't even intended, but it looks like you did. So systematic form means that it's a generator matrix, the identity matrix on the left, augmented with some other matrix on the right. Now, there is a shortcut to this. This would not be something that we could do in real time with communications that need to happen fast. That's why we use the special case error correcting code. You read Solomon's and things of this nature. There is a shortcut. There's something called a parity check matrix. The parity check matrix essentially is the generator for the orthogonal complement to the code. And it will basically just tell you if there's any errors or not. If there is an error, then you still have to go through the process of checking. All right, so those are just the general basics of that. So what is the parity check matrix? Well, if we think about the parity check matrix, I already said that it generates the orthogonal complement. The orthogonal complement, if C is our original code, the orthogonal complement is denoted with a perp. So if we have a parity check matrix, we can take any code word we receive and multiply it against the parity check matrix. If it's a zero, we know there's no errors. If zero vector, we know there's no errors. If it's not, then we have to go through the search and figure it out. Well, it turns out that the parity check matrix is directly constructed from the original matrix. As you can see there with the G and H, if you have G in systematic form, where it's the identity matrix on the left and an augmented matrix on the right, you can see how H is created by using some transpose and reordering of the coordinates. Okay. Now, if we look down here at the very bottom, we can see that you'll end up with at the very end the reason why it works, the reason why it becomes a zero vector. Because if you take these, multiply it, you end up with the negative this transpose plus the positive of it, and you get the zero case. Now, there are situations where a linear code contains the orthogonal complement. We say that those are self-orthogonal codes, and there are actually cases where the codes are equal to their complement, to their orthogonal complement, and we say those are self-dual, and these are going to be the focus of the talk. Okay, so the structure of a self-dual linear code. Now, if we say that a self-dual code is equal to its orthogonal complement, there is a relationship between the length and the dimension of codes. Now, this is really out of the same thing, what you might say matrix theory, where the nullity of a matrix and the rank of a matrix, their sum has to equal to the dimension of it. So if we're going to say that the orthogonal complement is equal to the code itself, it must be the case that the dimension is half the length. And so that is an iconic feature of self-dual codes, is that their dimension is half the length. Now, their construction for their generating matrix is pretty interesting, because if you have an identity matrix on the left, the matrix on the right, the augmented one, is going to have the exact same dimensions. And as it turns out, if you look at the second line where we have what it means to multiply the generating matrix of the parity of the orthogonal complement and G, it means that G generates both the orthogonal complement and itself. So if you multiply G, of course, you have to go through the transpose to make sure it works out. You multiply it together, The right-hand side where my mouse is, you'll find out that the identity plus the transpose of A and the transpose of A, and this is the binary case, by the way, must be 0. This implies that the transpose of A times A has to be the identity matrix. These matrices are called orthogonal matrices. A matrix where you take its transpose as its inverse is called an orthogonal matrices. They're a very special type of matrix. And whenever you have a linear transformation through an orthogonal matrix, it respects Euclidean distances and angles. So if you had a polygon represented at where the coordinates are based like tuples, and you run those through the linear transformation, which is an orthogonal matrix, you would find out that the only thing the polygon does is just rotate, given that it respects angles or preserves angles and Euclidean distances. All right, so you may say, well, how hard is it to come up with an example of a uh, self-dual code? Well, it turns out the Hamming code gives us one right straight away. If you take the Hamming code and each row you add a parity check on the end of it, it turns out that you actually create a self-dual code. So if you look at the matrix G there, you see you have the identity on the left and you have an orthogonal matrix on the right, which means its inverse is its transpose. That's actually an order 2 matrix, which means that its transpose is itself. So it's a little bit degenerate in that way. So if we notice, this matrix generates a self-dual code, and this is called the extended Hamming code. In general, you can create a self-dual code by augmenting two orthogonal matrices. All right, so we've said that the length and the dimension have been shown to be related when considering a linear code and its dual. Are there relationships between the weight? Absolutely. For those of you guys, I think Vera Pless and Jesse McWilliams might have been actually computer scientists slash mathematicians. I believe one or both of those were involved with both. So if we look at the weight distribution, what is the weight distribution? Well, A0 is just the number of code words that are equal to 0. A1 is the number of code words with 1. A3 and so on is the number of code words with 3 non-zero coordinates. So if we look, this is the weight distribution for this code right here. There is one all 0. There's 7 of them with 3 set bits. There's 4 of them with 7 set. Sorry, there are 7 with 4 set bits, and there's 1 with all 7 set. Now, the weight enumerator is essentially the weight distribution represented as a polynomial. And the reason a polynomial is used is because whenever you have a direct sum of codes, it turns out that if you represent each portion of the direct sum as its weight distribution as a weight enumerator, which is a polynomial, then you can get the direct sums weight enumerator by multiplying them as polynomials. You can create a direct sum by using this. You could pad the left with zeros here, put G, the generator matrix for like the Hamming code. You could put the other G here and pad it over here with zeros. And the resulting weight enumerator generated by this will be equal to the product of the weight enumerators, which are polynomials. And that's an interesting thing. It's one of these things where, like, at first you think that is interesting until you actually work through it. Then you think, oh, there's no other choice for it to be that way. Isn't that kind of amazing how we learn and grow? We end up saying things, we find them fascinating at first, and then by the end of the day, we're like, oh, what else could it be, right? So Jesse McWilliams and Vera Pless, they came together. I don't know if they came together, but they developed what we say the relationship between the weight distribution between a code and its complement. And these are the equations. Jesse McWilliams developed 3 of them. And actually, the first 2 are essentially the same thing. And it turns out that all 3 of those are equivalent if you start playing around with plugging things in using substitutions. So if you look at the left hand, take this first equation. If you look on the left hand side, you're talking about the weight distribution for a particular code word, and you're talking about its complement on the other side. Same way with this one. And this one is more of a weight enumerator type thing. First 2 are dealing with weight distributions. The third one is weight enumerator. Then Vera Pless came around and she came up with the Pless power movements. As you can see, the left hand side only contains information about the code. The right hand side, you have the perp there, which means the orthogonal complement. Now, the reason the plus power movements are handy is you can actually determine the existence of a code if you go through and you keep working those equations, iterating over J's. In other words, those plus power movements, you can keep doing them until they finally degenerate into where you don't get anything else when you keep iterating through them. You'll see that sometimes you may end up with a negative value, and that wouldn't be possible. So you would end up saying this code doesn't exist because at some point the plus power movements give something that couldn't be possible whenever we only consider positive natural numbers for some of these things. Well, in the case of self-dual codes where the code and its orthogonal complement are equal to each other, it turns out that the weight distributions are equal. So if you look at the left-hand side, you look at the right-hand side, you end up creating a system of equations. And whenever you look for a solution for those systems of equations, you'll find out that you can sometimes take a code that's not known to exist, go through those, create the system of equations, and if you end up with a negative value in the solution, you know that code couldn't exist because the weight distribution can't be negative anywhere. So we're going to be talking about that just in a moment. So it's a very interesting case. Outside of self-dual codes, this is just kind of academic just to show the relationship, but it has a very strong correlation with self-dual codes, as we just said. Okay. Now, how many binary self-dual codes exist for a given length? So we're talking about the orthogonal matrices. Those are large in number. Now, we first have to talk about what it means to be permutationally equivalent. Two self-dual codes are considered permutation equivalent if one can be created by permuting the coordinates of the other one. So if you look at G and G prime here, you'll see that all I did, now remember, vector spaces are a set, so we don't care about the order of the vectors inside of it itself. So if you look, I actually transposed the first two coordinates of G and then switched the first and second row to create G prime. We say that G prime is permutationally equivalent to G. In other words, there's so much structure there that we don't even care that they look different. They're essentially the same structure. There's nothing about them different enough to really call them different codes. Now, this is very handy. We can essentially create, well, we got a mass formula. So we may say, how do we know how many self-dual codes there are? Well, actually, this is something that I have done. I've cataloged all of them up to length 36, and I normally a large database at this point. So if I consider that I can create every self-dual code has a systematic equivalent code, which means its generator matrix can be written in the form A augmented or I, the identity matrix, augmented with another similar sized orthogonal matrix. That means that I can essentially create all the self-dual codes if I keep iterating through the orthogonal matrices. So the number of orthogonal matrices is given by this formula that the product. Now, this grows incredibly large very quickly. You can check OEIS if you want to see somebody that has went through there. I actually think I provided the Python code for that on OEIS. How do we get beyond this? Well, it turns out that every code you generated, if it's a length 36, and that means there's 36 factorial equivalent self-dual codes to it because you can create 36 factorial permutations of it. But some of those permutations will not create just a permutation equivalent code. It will actually create the identical code. And whenever we say we're permuting the columns, we're essentially having a symmetric group, or we're having a permutation group act on the set of coordinates. So that's the action of what's going to happen. You're having a permutation act on the set of coordinates. And so if we have a permutation act on the set that creates the same code, we call that an element of the automorphism group. An automorphism is an endomorphism that is an isomorphism. Essentially, it creates the exact same thing, not just something equivalent. So for each self-dual code that we search and find, we calculate its automorphism group, divide that by n factorial, and so we have a mass formula. On the right-hand side, I've accounted for every possible self-dual code that can be created. On the left-hand side, for each code I find, I calculate how many permutation equivalent codes it will generate. And then we could tell once we reach an equality, we know that we have essentially counted and recognized all self-dual codes. Okay, so for example, G1 and G2 represent the only self-dual codes, binary self-dual codes of length 8. There's only two of them up to permutation equivalence. So we know that this one, where we have the identity augmented with this, I'll change it around a little bit, haven't I? Augmented with this orthogonal matrix, it has an automorphism group of 1,344. Whereas the other one, where it's just the identity augmented with the identity, that's an easy one to come up with because its automorphism group is just the cyclics, the direct sum of cyclic order 2 groups. So it's 384. So I take the 8 factorial, divide it by its automorphism group, and I say this matrix generates C1, which has 30 permutation equivalent codes. This one has 105. Looking at the mass formulas here, we add those two together and look what happens. We have accounted for all of them. Now there's 135 or length 4 orthogonal matrices up to end up creating just 2 binary self-dual codes of length 8. There are only 7 self-dual codes of length 16. However, there are 635 million orthogonal matrices. So that's self-dual codes, distinct ones, but only 7 of them up to permutation equivalence. Now, are there any interesting properties associated with binary self-dual codes? Yes. If we look at the code words and we only analyze the length 3 code words, these are these right here. These are all the ones of length 3. Now, if we look, each one of the columns just has a sum of 3. That is an iconic case that there may be, thank you, there's going to be 3 in each one of them. So if we look at the coordinates of that, we find out that they create a T design. And a T design is essentially a combinatorial design that can actually show whether a code exists or not. So this is a little bit of a different story, but I want to hop right now to the very last part of it since I'm almost out of time here. Are there any open famous problems in coding theory? Absolutely. The top 2 binary self-dual codes of the form 24K, 12K, and 4K plus 4 are only known to exist for K less than 3. The K equals 3 has been almost like searching for Ahab and the white whale. So the prize money right now is $200. And I told my father I was working on this. And so he sent me a check for $200. And he said, here, you must be on hard times, I suppose. He said, why don't you try doing go box conjecture or something? I said, well, thank you, Dad. Anyway, so we know that K cannot exist for greater than 154 because at that point, the systems of equations derived to make the weight distribution has a negative in the solution. So that's quite a big distance from where we are to where we have an upper bound. This code that's not known to exist, we know what the weight distribution of the code. So we don't even know if it exists, but we know what the weight distribution, we know how many of them each weight there will be. And right there it is. Self-dual codes have a symmetry, by the way. That's the reason you say A0 is equal to A72. The existence of this code would also imply the existence of a type 1703514 code. The weight 16 codes are a generating set. The weight 16 code words will form a 5 design, a combinatorial design. The automorphism possibility, so we don't even know if it exists, but we know which possible automorphisms and coordinates that we can switch to make it an equivalent code. You have a list there where it can't contain those. And I could probably find publications where they have at least probably that many more, maybe that many more 2 times over. So a discussion about my elements, I have basically went through and I run into a man at a conference one time and he gave me a suggestion and he says, you know, the work that you've done is actually quite impressive. He gave me some thoughts and I went to go speak to a former advisor of mine. I said, you know, I just met a guy after I gave my presentation and he gave me some advice. He said, that guy you're talking about is Neil Sloan. I had no idea that that was him, but he's kind of the guru man of self-dual codes, I believe. I think he's a computer scientist as well. So thank you for the time, and is there any questions?
Wow, well, that's an enormous amount of material to assimilate in a short amount of time. So I expect it'll take all of us who aren't experts in this particular subfield a lot of time to assimilate it. And unfortunately, we don't have that time right now, but anyone who would like to ask questions offline, I encourage you to do so. And certainly coding theory has a lot of applications within computer science, within communication. So I want to thank you very much for this presentation. It's good to see that mathematics is still alive in the world of computer science. And let me invite everyone then to the Keeping Current seminar next week, which we will then meet again, and hopefully the weather will be better, but we still won't be meeting in person. So thank you everyone for being here, and I'll see you next week.